Welcome back. So let's take a look at floating point addition. So we'll take a look at all three: floating point addition, multiplication, and division. So let's start with addition. Addition and multiplication are done almost similarly. Division is, however, different and it's very interesting. Alright, so let's quickly go back to chapter 2 and quickly do a revision of how floating point numbers are stored. So we'll use 32 bits, a 32-bit number system as the running example, but same results hold for 64-bit. So I'll not, in the cost of, not repeating, repeating the same thing rather, I'll not repeat it. So in a 32-bit number system, we share we store one bit. The most significant bit is the sign bit. So any number that has a normalized form. So the normalized form basically says that we take this number -1 and to the power s. So if s is 0, the sign bit is 0, means that this is 1. Otherwise, if the sign bit is 1, means that -1 to the power s is -1. So its number is negative. Then we store a significand. So the significand is of the form 1 point, a sequence of 23 zeros or ones. So the significand is greater than equal to 1, or rather 1 is less than equal to p and is less than 2. Then we have 2 times e minus bias, where e is the real so e is the exponent that is stored, and bias is 127. So for example, if you want to represent a number of the form, let's say 1.5. Okay, let me go maybe here. Let's say we want to represent a number of the form 1.5. So 1.5 in base 10 would translate to 1.1 in base 2. So in this case, the sign bit is 0. The sign bit is 0. Then we'll save a 23-bit Mantissa. The main reason being that the 1 here is common. So the 23 bits of the Mantissa. So go back to chapter 2 just in case you have forgotten what these terms are. So the 23 bit Mantissa will save 1 and all zeros, pretty much. And after that, we'll save the exponent. So the exponent is stored in the bias notation. And so if the exponent in this case is nothing, it's 1.1 times, it's 1.5 times 2 raised to the power 0, right? So the exponent basically is 0. So what we will do is that we will set e as 127, such that the real exponent is 127 minus the bias, which is 0. So that's pretty much so in a 32 bits, the way that we would store is that we'll have 1 bit for the sign, we'll have 23 bits for the Mantissa, then we'll have 8 bits to store the exponent, and the exponent is stored in the bias notation. The real exponent is actually e minus the bias, right? That's the real exponent. And we also mentioned that we have, so since this number can vary from 0 to 255, we also mentioned that 0 and 255 are used to hold special values. So in particular, if we use the value 0, right, so the last 8 bits are 0, it meant that it meant two things. If the significand is 0, then the number is 0. Otherwise, if the significand is non-zero, then it represents a special kind of number. So we will this special kind of number is called a denormal number. And we also said that if the exponent is 255, which is the highest value, and then if the Mantissa is all zeros, then it can either be positive or negative infinity. And if the mantissa is not 0, then it's not a number nan. So I'm not discussing these things in detail here because I've already spent a lot of time discussing these issues in chapter 2. But let me nevertheless just summarize. Let me just summarize that information that we require. So what we require is that any floating point number can be expressed in a normal form, where it will have a sign bit which will determine the sign of the number. Then we'll have a significand which is of the form 1 point, then 23 zeros or ones. So this part is called the mantissa, right? So it can be any combination of zeros and ones, but just 23 of them. And then we'll have an exponent. The exponent is stored in a biased notation, and the bias is 127. So we also took into account the fact that when the exponent when the exponent is 0, then we can have a special class of numbers called denormal numbers, where the standard form of a denormal number is like this. It's a number of the form as shown here. There's a small error in this slide. So instead of 1, it should be 0. So 0 is less than equal to p is less than 1. So as we can see, is that just where the range of normal numbers end. So let's say these are all the normal numbers. Of course, the graph is not drawn to scale, and let's say this number is 0. So we have a tiny buffer of numbers here called denormal numbers. And the standard form of a denormal number is that it's of a number of the type 2 raised to the power minus 126 times p times minus 1 to the power s. But here the significand has a different form. It's not 1 point something, rather it is 0.23 zeros or ones. Right? It's of the form 0 plus the mantissa. When the mantissa is 23 zeros or ones. Right? Some number, some combination of zeros and ones. Alright, so given the fact that we have seen this, we are now ready to, in a sense, take a look at the way that we shall do floating point arithmetic. So let us assume that we want to add the numbers a and b. So if we want to do that, let's take a look at the E field, and the E field is the value that is stored, right? So it is the real exponent plus 127, which is the bias. For example, when we try to save a number of the form 1.5, which is actually 1.1 in binary, then the real exponent was 0. So what we save is 0 plus 127, which is the bias. Let us now take a look at floating point addition. So let's first consider the inputs. So we are given two 32-bit inputs. So the format of the input is as follows, that we have a 1-bit sign bit, we have a 23-bit mantissa, and we have an 8-bit exponent field, where the exponent is stored in the bias notation. So if the real exponent is x, so what we are saving is x plus the bias. So if the real exponent is 0, then we are saving 127 because the bias is 127. Similarly, the B field is formatted in the same manner. We have a sign bit, we have a 23-bit mantissa, and we have a 8-bit exponent. So we need to add these two floating point numbers. The result will be another floating point number which is stored in exactly the same format. And we need to design an algorithm such that given A and B, we can compute C. So what we do is that, let me just describe the pseudo code of the algorithm. So what's a pseudo code? It's basically a list of steps written in a kind of high level description of what the algorithm will do. Then hardware designers can take this algorithm and implement a circuit in hardware. So let's do one thing. Let's unpack the E fields. And unpack meaning let's extract them. So let's call the E field of A as EA and the E field of B as EB. And let the E field of the result be EC. Similarly, let's unpack the significand. So the significant, recall that it's a number for normal floating point numbers. It's a number of the form 1.m, where m is the mantissa, and mantissa itself contains 23 bits. So it's a number basically of the form 1 point, 0, 0, 1, 0, 1, 1, 23 bits. So the 1 bit before the decimal point and the 23 bit mantissa make it 24 bits. Let's do one more thing. So let us then assign it to a number of the form w, where we add a leading 0 bit. So let's say, let me consider an example. Let's assume 1.5 in decimal. So 1.5 in decimal is 1.1 in binary. So in this case, the significand is 1.1 and the mantissa is 1 followed by 22 zeros. So we will define a number of the form w, where w is of the form 0, 1.1. So mind you, the point cannot be stored in binary, so we are only using it to enhance readability. So its position is implicit. So w thus becomes a 25-bit number quantity. And so where does this 25 come again from? Once again, the significand is of the form 1.23 mantissa bits. So the significand is 24 bits. And we add a leading 0. So this will become 0, 1.m, where this is 2 bits and this is 23 bits. So total it's a 25-bit quantity. So with no loss of generality, let's assume that EA is greater than or equal to EB. And let's call the significance of A and B as PA and PB respectively. Furthermore, let's define a temporary variable w, which is of the same 25-bit form that we had discussed in the last slide. And let us get it by unpacking the significand of b, which has this smaller exponent. So let's unpack pb and get w. So now let's take a look at the way that we want to do the addition. But before that, let me motivate you by saying how we would do it in the case of decimal. So let's assume I want to add 2 times 10 to the power minus 1 plus 4 times 10 raised to the power minus 3. So I would first in a sense unpack it. So this would be 0.2, this would be 0.004. Subsequently, what we will do is I will write it in such a way that the decimal points are aligned. Then we will go forward and do the addition. So what we need to do in a similar, so there's also another way of looking at this. Let me maybe erase part of it. So in this case, the exponent of this minus 1 is greater than minus 3. So instead, what I can do is that I can write this as 2 raised to the power 10 to the power minus 1. No problem with that. However, this can be written in a different way. This can be written as 0.04 times 10 to the power minus 1. So 10 to the power minus 1 part being common, I can just write it in the side, and then I can add 2.00 and 0.04 to make it 2.04. And then so the final answer is 2.04 times times 10 to the power minus 1. Alright, so what we can do is that we can do something similar. We can first make their exponents the same, and then we can align the decimal points and perform an addition. To make the exponents the same, what we would do is that we will make the exponent of b the same as the exponent of a, and the exponents can be made equal by shifting w to the right by ea minus eb positions. So this is a simple, very simple thing. So ea minus eb is the difference in exponents, and so what we will do is that if we shift w to the right, by these many positions, then effectively we'll be multiplying 2 to the power EA minus EB with EB to make it to the power EA. So then we will have, we will be able to align the decimal points and add. Right, so this is the first thing. In any floating point addition, we always align the decimal points. Aligning the decimal points essentially means that we make the exponents the same and we write it in such a way that we can just do a normal addition. So we are doing exactly the same thing. We are setting the exponent of a and b to be the same, and this we are doing by right shifting w by ea minus eb positions. Subsequently, now that their exponents are same, so their exponent field for both of them is ea, and the real exponent is of course ea minus the bias. So that's fine. So then what we can do is we can do w equals w plus pa, which means that I'm adding the significand of pa plus the significand of pb, in a sense right shifted by ea minus eb positions. So this is the same as equivalent to aligning the decimal points, setting the exponents to be the same and adding. Now let the significant, so basically register W now contains a result of the addition, the result of the addition. So let the significant represented by register W be PW, right? So this is the significant that's there. This will be at the form, something point something, right? Where the position of the point is implicit or can be inferred. So there is a certain possibility that PW can be greater than or equal to 2. For example, if you're adding 1.5 and 1.5, so which is actually 1.1 and 1.1 in binary, so then what's the result? 1 plus 1 is 0, 1 plus 1 plus 1 is 1.0. Okay, so where we consider all these points to be aligned, so the result is essentially 3, and this is greater than or equal to 2. So this is not a valid significant for us. So in this case, we need to do something called renormalization, which is basically what we do is that we right shift. So 1.0 we make it 1.1. This is done by right shifting w by one position, and we increment the exponent ea, because ea is now the exponent of both. Ea is the exponent of the result. So we increment the exponent by one position. So let me give a similar example in decimal. Let's assume we have 23 times 10 to the power 4. But we don't want two digits to the left of the decimal place, the decimal point. So we can alternatively write this as 2.3 times. So essentially I'm right shifting it by one position and times 10 to the power 5. So I increment the exponent. So we are doing exactly the same in binary to ensure that our significand is between 1 and 2. So the final result is like this, that the sign bit will be same as the sign of A or B. So mind you, we are doing addition and we are thus assuming that the sign bit is the same. Right? So how do we define, how are at least we defining addition? We are defining addition by the fact that we are either adding two positive numbers or two negative numbers. If the sign bit is different, it will essentially become subtraction. So sign bit will be the same as sign of A or B. Right? So two positive numbers we add, the result is positive. Two negatives we add, the result is negative. Now we also have the significand PW and we have the exponent field EA. So given the fact that we have all three, we can construct a floating point number. So let me just quickly go back. So given the fact that we know the sign of the result, so let this be the result. So we know the sign of the result. So we know the significand. So from the significand, we can find the mantissa, right? The 23 bits after the point. And we also know the final exponent field, what it's supposed to be. So we can have EA over here, right? After doing these two steps. So let's explain with an example. So let's consider this example. Let's add the numbers 1.01 in base 2 times 2 cube plus 1.11 again in base 2 times 2 raised to the power 1. So the decimal point will be showing in W to enhance readability, but in the hardware it will not be there. So let's set A as 1.01 times 2 cube, and let's set B as 1.11 times 2 raised to the power 1. So the exponent in A will be greater than the exponent of B. And also, for the sake of readability, let's not use the bias notation for E, right? So let's also, avoid doing that. So let's not use the bias notation. Instead, let's assume that E is stored as is, even though in hardware that's not the case. So in this case, W will be 01.11, which is the significand of B. E is 3. E, the exponent of EA, the final exponent is 3. So to align the decimal points, what we need to do is that we need to right shift W 01.11 by 3 minus 1 places. Why 3 minus 1? Because 3 is the exponent of A and 1 is the exponent of B. So we need to right shift W by 2 places. So this will give us 0, 1, 1, 1 after the decimal point and 0, 0 before the decimal point. So now the decimal points of both A and B are aligned, and the exponent for both of them is E or EA, same thing, which is 3. So then we should add W with the significand of PA. So W is 0.0111 with the significand of PA, which is 01.0100. So if I do the addition, so let me see, plus I'll have 1, 1 here, 1 plus 1 is 0, it's 1 here, and 0, 1. So the final result is 01.1011. There is no reason to renormalize because this is between 1 and 2. So the final result C is 1.011 times 2 to the power 3, right? Because we are taking the exponent of A. So this is one example of how we would do it in hardware. Of course, we have made some simplifications. So we are not using the bias notation, but this should capture most of the idea. And the idea is simple. We are using exactly the same algorithm as we would have used for decimal numbers. So exactly the same algorithms and the same technique is being used, that we first make the exponents the same, then we align the decimal points and add. So let me consider one more example. So in this case, we are adding 1.01 in base 2 times 2 cube plus 1.11 in base 2 times 2 square. Again, the decimal point in W is shown for enhancing readability, and we will not be using the biased scheme, right? So that is what we'll not be doing. So A is 1.01 times 2 cube, B is 1.11 times 2 square, and the exponent of A is greater than the exponent of B. So the significand of B is 01.11, and E, the final exponent that at least we are planning at the moment, is 3. So to make W, the first stage would be is that we take the significand of B and shift it to the right by 3 minus 2 positions. So this will make it 0.111. Then we add 0.111, which is the value of W, the right shifted version of B's significand, with the significand of A, which is 1.01. So let's take a look at the addition. 1.010 plus 0.111. So 0 plus 1 is 1, 1 plus 1 is 0, carry of 1, 1 plus 1 is 0, carry of 1. So it's 10.001. So as we can see, this number is greater than 2, right? So it's greater than equal to 2, and that's a problem. So as a result, this needs to be fixed. The way that we fix it is that we sort of renormalize. So we shift it to the right by 1 position. So then this becomes 1.3 zeros and 1. And we increment E by 1. So 3 plus 1 is 4. So the final result that we have over here is 1.0001 times 2 to the power 4. So as you see that after doing the addition, there was a need to renormalize the result. And so what we did is that we right shifted W and we added 1 to E. So we added 3 plus 1 and made it 4. Let us now discuss a very tricky issue in the world of floating point math. So let's discuss rounding. So assume that we were allowed only 2 Mantissa bits in our previous example. So let's go back. So assume that here, right, we are allowed only 2 Mantissa bits. So we can store only 1.00 and we need to discard these 2 bits. So well, if it's 0, 1, maybe we can discard, but assume that the final result was of the form 1.0011. It might have been inappropriate to discard 1, 1 without making a change in the 0, 0. So it would have been maybe more appropriate to round it to 1.01. So rounding is an issue, especially when the number of Mantissa bits is finite, and this issue has to be considered. So let us first define some normal standard terminology, and then we will talk about rounding. And why does rounding come? There's another reason. So the reason is that we are essentially right shifting. So initially, if I consider the significand of A, it is of the form 1 point, something for 23 bits, that's fine. But this is being added with W, which is the significand of B right shifted by a certain number of bits. So for all we know, this can be of the form 0, 0, 0 and then a certain number of bits. Let me just erase and clean this, right? And then 23 bits. So when we do an addition, it will be 1 point something, 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 it might be like greater than 23 bits. So there will be a requirement to stop this at 23 bits because that's all that we can store. And the remaining bits have to be discarded. But they should be discarded in a way that the result is the most accurate. And for that reason, we have to do some amount of rounding. So let's the terminology first. So consider the sum W of the significance that we have. And note that in hardware, we're not storing the decimal point, it is implicit. So in a sense that we know where it is, but it's not being stored. So the significand is pretty much being stored as a 24-bit number in hardware, right? So it is, in reality, it is 1 point, the Mantissa, which is 23 bits. But the way that the significand is being stored in hardware is one continuous sequence of 24 bits. So it can be, alternatively interpreted as a 24-bit unsigned number. So let's use that interpretation over here. And so this is all that we can keep. We don't have space to store anymore. But it is possible that during our operation there will be some additional bits which actually have to be discarded. So let us do one thing. Let's assume that this is, let's logically assume that this 24-bit significand is one kind of number and the bits that are being discarded is another number. And let's say that the final number W is P plus R times 2 to the power minus 23, where if I multiply the significand with 2 raised to the power minus 23, the decimal point will come here just after the first bit. And let's define the R portion, the residue, as the part that we'll ultimately throw out, right? So the residue, we can treat it as less than 1 in this particular equation because we are assuming that since we are taking 2 to the power minus 23 out, the decimal point from this point has actually moved to this point, right? So that's what we are assuming. So any number will have a regular significand and a residue, and the residue part is thrown out. So we want to round the significand in such a way that it reflects the residue correctly. So, the terminology again, P represents a significant and the temporary result. It's stored as a 24-bit unsigned number, right? That's P. And we are storing the residue as a number which is strictly less than 1. So the aim is to modify P to take into account the value of R and then we can happily discard R. For example, if let me give an example in the world of decimal numbers. So let's assume we are allowed to store only 2 digits after the decimal point, and the number is of the form 10.5093. So since these two are the residue, they can be discarded, but we should update the significant to make it more accurate, which will be 10.51. So that's exactly what we want to do. And then, so in this process, we have created a new significant, which is P dash, and P dash reflects the residue correctly, right? Because the residue cannot be stored, we don't have the space for it. So IEEE 754, which is the floating point standard that we have discussed in a fair amount of depth in chapter 2, has several rounding modes. So let us discuss what these rounding modes are. So one rounding mode is called truncation. So truncation basically means that P dash is equal to P. So we just get rid of the residue. So let's say, I have, I can save, um, I'm sorry, yeah, I'm not allowed to save even a single digit after the decimal point. So in this case, what I will do is 9.5, I'll just round it to 9 and I'll completely discard the residue. In this case, I will discard 6 and even 9.6 I'll round it to 9 and even 9.99 I will round it to 9. So I'm just truncating, I'm just discarding the residue and I'm not updating the significand. So this is a very simple mode of rounding, and this is typically not advisable to use, but we can use it if you want to. So this is called truncation. The other is rounded to plus infinity, which means that we add the residue to the significand. So mind you, once again, the significand is a 24-bit unsigned number and the residue is less than 1, right? So basically, if we'll add both of them and we'll take their ceiling. So the ceiling operator essentially takes you to the next higher integer. For example, the ceiling of 3.4 is 4. The ceiling of minus 6.2, right? The next higher integer is minus 6. So pretty much we'll take the ceiling of the value. So 9.5 we'll round it to 10 because that's the next higher integer. Minus 3.2, if we have a number of this type, we'll round it to minus 3 because that's the next higher or greater integer. So this is rounding to plus infinity. So this also is something that can be done, is supported by the IEEE 754 format. And the advantage here is that we always choose the higher integer. So for example, what we are doing is we are considering a 24-bit significand. And then so since we have taken 2 to the power minus 23 out of the equation, I'll just go back. So this equation is the crux. And we need to ensure that all of us are understanding it. Otherwise, it will cause a little bit of an issue. A lot of issue, rather. The spirit of this equation is as follows, that in the course of our algorithm, we will produce intermediate results which are more than 24 or 25 bits, can even have 40 bits. So they will have a certain significant part which is of the form 1 point something, and then they will have a certain residue part. See, if I take 2 to the power minus 23 out, then pretty much what happens is that the decimal point, since the significand was of the form 1 point something, the decimal point is going to move from this point to this point. And so thus we'll have a purely positive number, a pure integer, not positive, but a pure integer called P, which is 24 bits, can be more, it doesn't matter. It's a pure integer, does not have a decimal portion, and a residue which is after the decimal point, and the residue is thus less than 1. So our aim is to consider P plus R, our aim is to consider P and R, both of them, and come up with a new significant P dash and discard R. So to discard, R will anyway have to be discarded, but we will have to see how can we take the effect of r into account, if r is small, we can get rid of it, but if it's large, then p has to be incremented, so some rounding has to be done. So our aim is to move from p to one more significant p dash and discard r, and but take the value of r into account. So we discussed truncation, we have discussed rounding to plus infinity. So one more method is rounding to minus infinity or negative infinity, which means we go to the lower integer. It's the opposite of rounding to plus infinity. So in this case, what we do is that we actually go down. So from 9.5 we go down to 9, and from minus 3.2 we'll go to the lower integer, which is minus 4. So mathematically represented, we'll add r to p, and we'll take the floor of the value. So floor means go to the lower integer. For example, 4.6, the floor is 4. Minus 3.8, we go to the integer that is lower than it, that is minus 4. In fact, even for minus 3.1, we go to the next lower integer, which is minus 4. So what are the three modes that we have discussed right now? Straightforward truncation, round to plus infinity, and round to minus infinity. Now we will discuss a slightly more sophisticated mechanism, which is also more popular. So in this case, what we do is that we said p dash is equal to p plus r. So actually some function of p plus r. So we'll discuss this function. It's called the box function, but we'll discuss this function in detail. So what we'll do is that we'll round it to the nearest. It's called round to nearest. So we'll round it to the nearest integer. So 9.4 will become 9, and 9.6 will become 10. Alright, so 9.4, the nearer one is 9, and 9.6 will become 10. Similarly, minus 2.3, the closer integer is minus 2. So that's fine. But the difficulty comes with 9.5 and minus 3.5, because they are in the middle. So what we will do is we will always prefer, we will round it. So 9.5 can be rounded to either 9 or can either be rounded to 10. So it's equally, close to both 9 and 10. So in this case, what we will do is, as a matter of convention, we'll prefer the even number. So even number is 10, so we'll round it to it. Similarly, for minus 3.5, we'll round it to the nearest even number, which is minus 4. So what is round to nearest again? Round to nearest is that if the number is not of a form x plus 0.5, we round it to the nearest integer. However, if it's a number of the form x plus 0.5, then we choose the integer that is even. Right? The nearest integer that is even. Let's now try to summarize the rounding modes. So the rounding can be thought of as a function. So the inputs of the function are like this. So let's first draw a black box. So what goes in is the significand as an unsigned number, as a 24 or 25 bit. It does not matter, but what goes in is an unsigned number, which is the significand. And so actually even before this, we compute the final output w, and then we extract the significand, which is pretty much the amount that we can fit with a 23-bit Mantissa. So it should be of the form 1 point something, and the Mantissa is over here 23 bits. So that is our significand, which we have extracted out of the final result of the mathematical operation, right? Be it addition or subtraction, but we'll talk about just addition with the same signs for the time being. Then what we do is that we send this number, which is actually a 24-bit number, as the significand, and we also send the residue, which is less than 1. What comes out is the new significand, p dash. And so p dash, there are two choices. One is p dash is equal to p. So that is a default. So here basically we set the residue to 0. The other choice is that p dash is p incremented with 1. So p plus 1. Right. So in this case, we have effectively done some rounding. So in this case, we are incrementing the significand. So let's now try to state the basic rules for different rounding modes. Let's consider truncation first. So in the case of truncation, what we do is we completely discard the residue. So p dash is equal to p. So in both the cases, we don't do anything and the default remains. And the default, when the sign of the result is positive and when the sign of the result is negative, is the same, which is that we just discard the residue. So that's the reason we don't do anything other than mere truncation. Let's now talk about rounding to plus infinity. So let's take a look at two numbers, 3.1 and minus 3.1. So in the case of 3.1, this needs to be rounded to plus 4 because that's the next greater integer. In the case of minus 3.1, this needs to be rounded to minus 3 because that is the next greater integer. So the conditions are as follows: that if the sign of the result is positive and we have a non-zero residue, which is exactly this case, then what we need to do is we need to increment the significand. So we need to increment 3 to 4. Otherwise, if the residue is 0, anyway we don't need rounding, so we can leave it as is. If the sign of the result is negative, as in this case minus 3.1, in that case, so basically if I draw a number line, minus 3 will lie here, minus 4 will lie here, and all intermediate numbers will lie over here. So since we are rounding towards plus infinity, all the numbers will be rounded to minus 3. So what we are essentially doing is that if this can be any number of the form minus 3.x, we will truncate this x and we'll round everything to minus 3. So essentially we need to let the default happen, which is that we set p dash equal to p and discard the residue. Let us now, after a brief cleanup of course, let me clean this part up. Let's now talk about rounding to minus infinity, which means choosing the lower integer. So let's again take a look at 3.1 and minus 3.1. So in the case of 3.1, we need to round it to 3. So even if so let me draw a number line. So let me have, let me have 4 over here and 3 over here. So all the numbers between 3 and 4 will get rounded to 3. So what we are doing is that when the sign of the result is positive, we are discarding the residue. So that's the reason we can do our default action here. However, if the number is negative, then so let me draw a number line. Let me write minus 3 here and minus 4 here. So minus 3.1 would stand somewhere here. So for all such numbers, what we need to do is that they need to be rounded to the lower integer, which is minus 4, right? So the logic is that if there is any non-zero residue, which means that the number is somewhere in this range, then we need to perform a rounding, which means increment the significand. So what we need to do is we need to check if the residue is non-zero. If that's the case, then we will increment the significand. And from minus 3, we'll take it to minus 4. So once again, just to refresh, for all the empty entries, we never increment the significand. Rather, we fall back to the default, which is to discard the residue and keep the significand as is. Wherever there is a condition, if the condition is satisfied, then only we increment the significand. So let us now discuss the last rounding mechanism, which is round to the nearest, which is also, by the way, the most complicated. So just give me 1 second. Alright. So rounding to the nearest is the most complicated, but it's not that hard. So let's see. So let's assume that I have 3 numbers, 3.1, 3.5 and 3.9. So 3.1 I need to round to 3, 3.5, I have a choice between 3 and 4. I choose the even number, so I round it to 4. And 3.9, the closest integer is 4. So the logic is like this. I'll first take a look at the residue. If the residue is greater than 0.5, as in the case of 3.9, then I will increment the significance. I'll increment 3 to 4. Otherwise, I'll take a look at the other condition, which is that the residue should be equal to 0.5. So in this case, the residue is equal to 0.5, and the least significant bit of p, which is the significand, is 1. So what this basically means that p is an odd number. So recall that what I'm trying to say is an odd number implies that it's, implies, and also it's implied back, that is least significant bit of that number. So in this case, p is equal to 1 in binary. And the reason is very simple, that in this binary notation, for an even number, so since this sums of powers of 2, for an even number, its least significant position has to contain 0, because the rest of the numbers are a power of 2, multiples of 2 essentially. And for an odd number, the least significant bit position should be 1. So what we are essentially checking here is that we are checking that p is an odd number. So in this case, the significant p is 3, which is an odd number, and the residue is 0.5. That's the reason we are incrementing 3.5, we are rounding it to 4. If I would have rather considered 4.5, then the first subcondition would have been true, that the residue is 0.5. However, the significant p would not have been odd, so this condition would have evaluated to false. Hence, we would have not rounded it, and we would have rather truncated it, and the answer would have been 4. So this is the case when the sign of the result is positive. So let us now see what happens when the sign of the result is negative. One second. Okay. So let me again consider the three numbers, minus 3.1, minus 3.5, and minus 3.9. Right, the negative variance. So what I do is I'll take a look at the residue. If the residue is greater than 0.5, I'll do something, or if the residue is 0.5, I'll do something else. But both the conditions for this number are false. That's the reason I'll truncate. So minus 3.1 will become minus 3. Now if I take a look at minus 3.9, the first condition is true. The residue 0.9 is greater than 0.5. That's the reason we'll increment the significand, and this will get rounded to minus 4. Now if I consider minus 3.5, well, so in this case the residue is 0.5, so this subcondition is true. Again, what I need to check is that p is an odd number. If it's an odd number, something needs to be done, otherwise we can go with the default. So in this case 3 is an odd number, so that's the reason we round it to minus 4. Had it been minus 4.5, then this condition would have been false, because 4 is an even number. So instead we would have rounded it to minus 4, which is exactly what we want to do in this particular scheme, that we always want to round it to an even number if the residue is 0.5. So these are all the conditions for all the 4 rounding modes. Truncation, which means do nothing. So do nothing means keep the significand as is, get rid of the residue. In all cases we get rid of the residue, but here we keep the significand as is. Round to plus infinity, we check if the residue is non-zero. And of course, if the sign is positive, the sign is negative, again we do nothing. And round to minus infinity is just the reverse of round to plus infinity. Round to nearest is somewhat tricky. There are two cases. We need to check if the residue is greater than 0.5, we increment the significand. If the residue is 0.5 and the significand is odd, then also we increment. And this is the same condition for both positive as well as negative results. So one very important takeaway point here is that to implement this in hardware, we have to have multiple circuits. So the first circuit needs to compare the value of the least significant bit of P with 1, right? So you need to have one comparison circuit. That is one circuit that you need to have. The second circuit needs to compare the residue with 0 and compute this expression. The third circuit needs to compare the residue with 0.5 and see if the residue is greater. And fourth, you need to compare the residue with 0.5 and see whether it's equal. If we can compute the values of all four of these expressions, then we can compute all the rounding conditions. So this is exactly what we need. We need the least significant bit of P. So this is very easy to get. I'll not discuss this, right? It's just one bit has to be extracted. But to get the rest, it's somewhat tricky. So what we will do is we'll add a couple of more bits to get what we want. So let us consider the residue R and let us refer to its most significant bit as R, or the round bit. So if I consider, this as the residue, so let me consider its most significant bit, let me call it R, and let the logical OR of the rest of the bits of the residue, OR of all of these bits, just a simple OR operation, let me refer to this as S. So if S is 1, it means that at least one of these bits is 1. If S is 0, means that all of these bits are 0. So I claim that just with R and S bits, we'll be able to evaluate all the conditions. Let's see how. So R greater than 0. So if R is greater than 0, it means that at least one of the bits in the residue is 1, which means that either R is 1 or S is 1. If S is 1, means one of the bits here should be 1, has to be 1. So the condition is we just do R or S is equal to 1. If this condition is true, it means that one of the bits here is 1, and we can infer that the residue is greater than 0. Now let's consider one more case where the residue is equal to 0.5. If the residue is equal to 0.5, it means that the round bit is 1, because it's pretty much less than 1, so we have 0 point here before it, which is implicit. So what is the representation of 0.5 in binary? It is 0.10000, right? So basically the R bit will be equal to 1, but all of these bits will be equal to 0, so their OR will also be 0. So the condition will be that R is 1 and S is 0, so this can be inferred as S bar, S complement is 1. So this is the condition, R and S complement is equal to 1. The last condition is R is greater than 0.5. This will happen when R is 1 and at least one of the bits in the, at least one of the rest of the bits is equal to 1. So then the OR function will evaluate to 1, so the S bit will be 1. So basically the function here is that both R as well as S, both of them need to be 1 for the residue to be greater than 0.5. Why is this again? Because any number greater than 0.5, its binary representation has to be of the form 0.1 and then can be anything else, but among these bits, at least one bit has to be 1. So then we can say that the number is greater than 0.5, and if one of these bits is equal to 1, then it means that their OR is 1, so S is equal to 1. So the condition is that R is 1 and S is 1, so R and S is equal to 1. So we thus see that keeping the R bit or the round bit and the S bit as the sticky bit, just computing them when our output is being created, will help us get all the conditions to implement all the 4 rounding modes. Let's look at the process of rounding in a little bit more detail, one particular aspect that we have not talked about. So when we increment the significand, there is a possibility that we might have to renormalize once again. The reason is that the significand might become greater than equal to 2. After renormalization, it's again possible that the exponent field E becomes equal to 255 which is actually an invalid value because 255 can signify two things, either not a number or plus minus infinity. In both cases, it's not a valid number. So we need to declare an overflow, which means that the number, the result, cannot be represented with the number of bits that we have. So essentially the number overflows the range of the number system. So let's now look at addition of numbers with opposite signs. So in the world of signed numbers, we technically don't have a difference between addition and subtraction. That's the reason we have classified our discussion differently. We have said that let's consider numbers with the same sign, and let's consider numbers with the opposite sign. So if I consider numbers with the opposite sign, the algorithm is more or less similar, a little bit of difference in some places. So with no loss of generality, let's assume again EA is greater than or equal to EB. So the first few steps are the same. We load the register W with the significand of B, PB. So since A and B don't have the same sign, we need to essentially ensure that they have the same sign. And this can be done by negating B. So we take the 2's complement of W, so essentially set it to minus B. And then we'll perform an addition. The next step would be to align the decimal points. So to align the decimal points, what we do is we do the same thing that we did in the case of numbers which had the same sign, which was that we right shift W by EA minus EB positions such that their exponents are the same and the decimals are aligned. Subsequently, we add W with PA, so this will complete our addition. So we do that, and so recall that till this point everything is standard. So even if, let's say, we were to add two numbers with opposite signs in regular arithmetic, so since the significand is positive, let one number be A and let the other number be B, and B is in this case less than 0. So what we would do is we would add A with the 2's complement of B. Right, the 2's complement of B. That's exactly what we have done. We have taken the 2's complement of W, which contains the significand of B. We have aligned the decimal points, then we perform the addition. Now it is possible that when we perform the addition, the result might be less than 0. So why would this happen? Well, a simple reason that this would happen is that, let's assume one case where you're adding, let's say, minus 1, minus 1 point, sorry, let's say we are adding 1.1 with minus 1.5. So in this case, the exponents are the same. So the first one can be A and the second number can be B. So then we will see that the sign of the result will be negative. So that's the reason. So it's very easy to handle this case. We'll essentially replace W with the 2's complement of W. So basically we'll replace it with minus W. And we'll flip the sign of the result. Rather, we'll flip the sign bit of the result to indicate that so initially the sign bit will be the sign of A, but if after addition the result is negative, then what we will do is we will replace W with minus W and flip the sign of the result. So in this case, initially the sign of the result is positive, but since we get minus 0.4 over here, we will flip the sign of the result, so it will become minus, and pretty much the Mantissa significand and exponent will encode 0.4. So after we perform the addition and adjust for the sign, we need to normalize the result. So there are some reasons why we need to do that. Let us assume that we are trying to add these numbers. So the result will pretty much be 0.01, right? So this is not a valid significand. The reason it's not a valid significand is basically because it's not at the form 1 point something. So this is one of the cases where the result w is less than 1. So what we need to do is we need to keep shifting w to the left till it is in the normal form, which is 1 point something. So in this case the normal form would be 1.0. However, it will be 1.0 times 2 to the power minus 2. So what we essentially have to do is we have to keep left shifting w, or we have to keep shifting w to the left till it is in the normal form, and simultaneously we need to decrement the exponent EA till we reach the normal form. So in this case we'll have to decrement the exponent EA by 2. After that, the rest of the procedure is the same. We need to round numbers. Well, so rounding in this case is not really required, because if you are shifting to the left, then we are essentially shifting in zeros, but otherwise it might be required, especially if the exponents are the same and some bits are remaining. So we need to round and renormalize. Alright, so once we have discussed all of this, let us summarize our entire discussion in a flowchart. So the flowchart looks at all possible cases. So let's assume that we are trying to add a and b, two floating point numbers a and b, and the result is one more floating point number, which is c. So they can have the same sign or they can have different signs. So the first check that we should probably do is check if a is 0. So if a is 0, it's a simple case. The result is equal to b. If that's not the case, we can check if b is 0. If b is 0, again it's a simple case. So we can set the result to a and move forward. Then we need to swap a and b such that EB is less than equal to EA, or EA essentially has the higher exponent, right? So we need to ensure with no loss of generality that EB is less than equal to EA. If that's not the case, we'll just swap A and B. Then what we do is that subsequently what we do is that we align the decimal points. So what we can do is we can perform this step. So in this step we align, so we set the exponents the same and align the decimal points, and this is achieved by essentially setting W as PB right shifted by EA minus EB positions, and we set EA, the exponent of A, as the default exponent of the result, and the sign of A as the default exponent of the the sign of A as the default sign of the result. So recall that in our discussion the order was slightly different, but I'll come to it. Then we check if the sign of A is equal to the sign of B. If that's the case, then well, that's great. So we just add W, we just set W as the old value of W, which is the significand of B shifted to the right by some places, plus the significand of A. So we just perform the addition. Otherwise, we take the 2's complement of W and then we perform the addition. So recall that we had reversed the order of this step and this step in one of our previous slides. So it technically does not matter if we have enough number of bits, because we are not losing precision. And when we are inside the hardware, we are not limited to have 32 bits. We can have more bits because they are after all temporary spaces, right? So the constraint is that the inputs will be 32 bits, right? And the output also needs to be 32 bits. But inside the circuit, we can definitely represent the significance and the mantissas with more number of bits, and later on discard some bits using a proper rounding policy. So that's the reason the order of right shifting and 2's complement does not matter, and as long as we have sufficient space, which anyway we have, or we are assuming to have. So after performing the addition, especially if the signs are different, there is a possibility that W is less than 0. If this possibility is there, that W is less than 0, then if this is the case that W is less than 0, well, then we again replace W with the 2's complement of W, and we flip the sign bit of the result, the sign of the result, right? as we had showed in the previous slide, that when the result was minus 0.4, so we actually set the significand to 0.4, I mean 0.4 properly adjusted, and we flip the sign of the result. If it's not the case, we can directly move over here. Then we normalize W and bring it to the standard form, and also update the exponent E. At this point, it is possible that we can either have an overflow or underflow. What this means is that we might have exceeded the range of the number system. So this should be reported as an overflow. Then we need to perform a rounding because the Mantissa can only be 23 bits. The additional bits have to be discarded. So we need to round. After rounding, we need to renormalize W and update E. And the process of renormalization itself can induce an overflow or underflow. So this should be reported. And if we have reached this step, means everything is in order. So we need to construct the result C out of W, which is the the final significand. So we can construct the Mantissa out of it, the exponent field, and the sign bit, and then we report the result as C. So I would advise all the students to take a look at this flowchart in great detail. The flowchart is otherwise very simple as long as all the individual steps are understood, but it is very, very important to understand each and every individual step. Alright, so now let's discuss floating point multiplication and division.